again for organizing this. It's a nice meeting, actually. And we're going to follow a different path, I think, here. But what we're about to say connects to the previous informal discussions that I heard with pleasure before. First of all, we will start by introducing the attitude and methodological position that we're trying to use. Then this will be the task of Emanuele, namely to offer a brief overview of algebraic quantum field theory. And then we will ask what is the most reasonable ontology for the theory, namely particles or fields. And finally, we will describe whether it is possible to abandon this dichotomy to endorse some sort of tracular realism. And we will then put forth our claim, which is not so new with respect to non-relativistic quantum theory. Namely, we think that complementarity is the best way to understand the theory. By Emanuele. So the main problem, I think, that we were trying to understand is, what is quantum field theory about? Every physical theory is about something, unless we want to believe that it's a simple recipe to make calculations. But I'm sure that none of us here is in favor of this view. You have very many options here, a little bit like it happens in the non-relativistic case. For instance, we can start with a very general statement that you find in many textbooks, namely, particles and waves are oscillations of the quantum field. So this is a standard view, so to speak. The field is fundamental. Then Emanuele will introduce 4 theorems that seem to defend an ontology of fields, like in number 1. Then we will basically leave the bone mechanics, on the side, because field or particle, it really depends on what kind of formulation you choose. But in the end, we will basically analyze and discuss Baker's theorem, actually, so that it will be a rigorous result. Emanuele, I think it's now your turn. Try to.
Well, yes,
basically, because I anticipated our conclusion, our main thing, which has already been suggested by Michael Reddit already some years ago, as you can see. So, Emanuele, the stage is yours. And
okay, so just few words why we decide to dedicate this talk to algebraic quantum field theory rather than in the conventional quantum field theory. And actually, there are 3 points here. The first one is just because some of the theorem we are kind of discussing later in the paper should also hold for quantum field theory in its conventional and standard approach. Also, another argument that is commonly used in that kind of debate is that the axiomatic and hierarchical mathematical structure of the algebraic quantum field theory makes, in a sense, the interpretation task easier, just because it gets rid of all the mathematical problems concerning, for instance, renormalization or the F matrix or that kind of problematic issues that are not so present in algebraic quantum field theory. And also, even though Wallace, some years ago, David Wallace claimed that actually this theory doesn't have make new prediction, we consider the fact that a new reformulation of a theory, as this is, should don't need to make new real predictions. So this is just the justification part. Let's now have a brief overview of algebraic quantum field theory. And of course, first of all, we have to say that algebraic quantum field theory is a theory which main object of studies study, are the algebra observable, which are associated to bounded region of space-time. These algebras are sister algebras that have to be satisfy 4 axioms, at least according to the Haag-Kastler formulation, which is the first and most basic formulation of the theory. Of course, it's possible to have different, slightly different formulation, but this is the most standard algebraic quantum field theory. So the first axiom is isotony, and the idea here is that if we have an observable that is measurable in a space-time region O1, and then we have a larger space-time region O2 containing O1, that observable continue to be observable and measurable also in the larger region. Then we have microcausality, that is the idea of locality by which we prescribe the algebra, the observable of the algebra associated to space-like separated space-time region to commute. So as you can read, all the observable associated to the space-time region O1 are required to commute with the observable of another region associated to a second space-like region O2. Then we have a translational covariance that is just the algebraic way of translate this kind of symmetry, translational group symmetry, in the algebraic machinery. So the idea is that translation is represented by a translation group in the group of automorphisms of the algebra, containing all the morphisms that leave the states of the algebra unchanged under that kind of symmetry. Then we have the last of our axiom, that is the spectrum condition. And this spectrum condition ensure us and give us the ensure us that no negative energies can occur. Okay, we have to list two couple notion more. The first one is the notion of representation, because till now I have spoke just of sister algebras and abstract algebra. But in order to have more concrete, let's say, algebras, we have to represent that algebra with a map that associates every element of the abstract algebra with the set of all bounded operators acting on the Hilbert space. The resulting Hilbert space, so the space that we have after this representation procedure, is called the representation space. And one important, really important notion is the notion of irreducibility. So in technical terms, it means that if a representation space has no closed invariant subspaces, is irreducible. Why this is so important? Because commonly and usually this notion of irreducibility is taken as representing fundamentality. So if we have an irreducible system, it represents a fundamental system of our physical theory. And now there are the first problems. Why? Because, of course, one of the first results of algebraic quantum field theory is that when we try to represent our abstract algebras in the representation space, so in the Hilbert representation space, we can have many inequivalent irreducible representations. So we will have different representations of the same physical system, all of them irreducible, but many of them inequivalent. So the problem is that we will have different representation of the same physical system and no criterion to decide which is the right representation among them. In quantum mechanics, in standard quantum mechanics, this is not a big problem. Even if we want to use an algebraic approach for quantum mechanics, because there is a theorem that is called the Stofan-Neumann unique theorem that proves that all these unequivalent representations that can arise are actually up to unitarity equivalence represented by the same Hilbert space. The problem in algebraic quantum field theory is that this theorem is not longer valid when we consider infinite number degrees of freedom. And actually, this problem cannot be solved thanks to the Stoff-von theorems. And actually, this is one of the problems we will discuss later in the talk. So, till now, so far, for what concerning the structure of the theory. Now, we want to address two alternative ontology, the first one in terms of particles, the second in terms of fields. And I would like to, to present a list of theorems that seems to, on the one hand, undermine the notion of particle, and as we shall see, also the notion of field. Let's start from particles. A particle, to a common understanding, should be something that is countable and that is a localizable entity. I mean, I have to know where the particle is localized. Actually, there are a series of theorems against countability, for instance, X theorem and Rich-Leader theorem, and against localizability. Rich-Leader is mentioned twice because it has two understandings, one concerning countability and one concerning localizability. Then there is also Malaman theorem that is explicitly about the impossibility of localized particles. And finally, we will discuss another result that is called the Unruh effect that show, or perhaps seems to show, that a system described by any quantum field theory, also algebraic quantum field theory, could be representation dependent. We start from the Hughes theorem. So, in quantum field theory, we would have a structure that is called Fock space. The Fock space is a space that is a direct sum of single particle Hilbert spaces. So it's the construction, it's the so-called second quantization to construct a theory starting from the notion of particle. We can define operation and, creation and annihilation operators. And we can also find a very important tool that is the total number operator that represents the number of particles in a physical system. However, it's possible to prove that this total number operator is defined only for asymptotic free fields. So like for Fock space without interaction. When we discuss also interaction, it's not possible to use the same Fock space, and actually it's not possible to construct a proper Fock space either for interaction. So in a sense, this means that particles should be counted only in the free states, and so this total number operator is not possible. It's not possible to define this total number operator when integration are added to our picture. Of course, then there is also the Rich-Leader theorem that, apart from all the technicalities, it basically say that when we have an algebraic quantum field theory, and this is a theorem that is specifically contextualized in the algebraic approach, whether the other one, the other ones can be also used in conventional quantum field theory. Now, here the idea is that when we have an algebraic quantum field theory, we represent the algebra of the vacuum, so the basics, common ground of all the theory. We know that if this representation satisfies all the action we described above, this vacuum shows the property of cyclicity. This means that we can, by acting with an operator on the vacuum sector, approximate any other state starting from the vacuum. So what does it mean in a less technical way? It means that any operator is separating from the local algebra, so it's not really relevant only of the local algebra, but can have influence also on other states. And it is valid for all vectors with bounded energy. concerning our notion of countability and localizability, already read in 1995, show that if a local operator can never be an element of the algebra, of the local algebra, sorry, we cannot have local measurement operator. So we cannot have operator that can allow us to decide if we are looking at an end particle state or a vacuum state. Just because if we want to define a local number operator instead of a total one, we have to suddenly recognize that this operator is not part of the local algebra. So it gave us a non-sharp value. And actually, as I said, an operation, a projection operator cannot be element of the algebra, so it's not possible also to localize that projection operator. So we cannot define local number operator. We cannot also either localize that operator, and it seems again that particle could not be counted, or at least to a first perspective localized. For what concerning localization, then we have Malaman's theorem. We have also a couple of other results, but the idea, and Malaman is the most important one, is that if we assume an algebraic, a quantum field theory with reasonable relativistic assumption, like the idea that something that is localized for any observer, and that we have to consider locality. If we accept all these assumptions, we have to consider localization is possible. So it's not possible to localize in any relativistic quantum field theoretic system particles. Of course, there are some possibility to resist this theorem. Maybe we can discuss later on the discussion time. But actually, the upshot is that according to what we said so far, particles have problem concerning countability, Hug theorems and Rich-Schlieder theorem, and concerning localizability, partially for Rich-Schlieder theorem and mainly for Malaman's theorem. Now there is the last problem that we mentioned before, that is the Unruh effect. The Unruh effect is a very important result because he put in the discussion the notion of the inequivalent representation we discussed above. Just because when we describe a physical system starting from a vacuum state, we will describe it with a so-called Minkowski representation. Now, Unruh proved that when an accelerated observer passes through this Minkowski representation, will experience a thermal bath of particles. They are called Rindler quanta just because the accelerated observer representation is called also Rindler representation or Fulling representation. But this is quite weird because when we have a vacuum state, we should have a state and a system which is devoid of particles because it's a vacuum state properly. But now we have two representations of the same physical system that depend on the motion of the observer. One of them describing a state with no particles, another describing a state with a thermal bath of particles. So in a sense, it seems that the particle content of a physical system is dependent, or maybe could be dependent, on the motion of observer, or to say to the representation we use to describe that system. So maybe could be the first results. Okay, there are no particles. There are just fields. It's not quite easy because in 2009 Baker proved that the wave functional space, which is the representation space that we use to commonly representing a field ontology, and the Fock space that we mentioned earlier, and this is naturally considered as representing particle are actually represented by the same Hilbert space up to unitary equivalence. So maybe we have to consider the fact that they are just two representations, different representation, but of the same concrete physical system. And in a sense, Baker claimed that the field interpretation may perhaps be undermined by the same problem, or at least some of them, of the particle interpretation. This is because when we compare the field quantization, so the quantization starting from a field that led us to the field representation and the wave functional representation, or the second quantization, as I described above that will give us the Fock representation, they actually are the same equivalent representation of algebraic quantum field theory. The unitary equivalence of these two formalisms can be the ground for generalizing the problem of particle to also the field interpretation. Think, for example, of the Malaman theorem. Malaman theorem shows us that particle cannot be localized. Shifting from a particle ontology to a field ontology, we could say, for instance, that, when we have a field operator, that field operator should give our amplitudes to a certain space-time point, or to a certain small, arbitrary small part of space-time region. Actually, that operator cannot be localized either. So even if we shift from a field to a field ontology, we will not have localization also for field operator. Or think another example, the Unruh effect. Of course, considering particle, we will have the vacuum sector with no particle, then the accelerated observer with particles, and it is quite problematic. Also for fields, because when we describe the vacuum sector in field theoretic terms, we will have a ground state, so the minimal level of energy. But when we describe the same sector, the same vacuum sector, in the accelerated representation, so in the Rindler representation, the problem is the same, because we will have an excitation of the field. So we will have two representations that, on the one hand, on the particles, we will give us two particle contents depending on the representation. Here, in the field in the field ontology, we will have two representations that will give us two content of the field, two level of the energy of the field, let's say, depending on the representation again. So maybe we should consider the fact that also for fields, the things are not so easy in the algebraic quantum field theory domain. So to this problem, so no particle, neither particle nor field, there are two possible answers. The first one that I would like to address in the next 3 slides is the hypothesis that maybe we can shift to a structural realism, to a structuralist ontology for the theory. So the idea is that there are no particles, and no fields. They cannot be, for the problem we already seen, the fundamental entities of the theory in terms of ontology. Moreover, it's important to recognize the Schrieder theorem is also used, thanks to the vacuum cyclicity property we very briefly and sketchy mentioned above, show that the vacuum state is entangled across many space-like separated regions. What does it mean? It means that in an algebraic approach, we have a kind of global algebra that contain all the possible subalgebra, local subalgebras, and so all these local subalgebras are entangled among them, and the global algebra is the only real algebra that we have to consider concerning the vacuum sector, of course. And this, if it's true, of course, is also is important also to mention the fact that this is the case because in algebraic quantum field theory, the algebra and the C-star algebra and the representation we are using are type 3 factor algebras, and this kind of algebras have no possibility of defining finite abelian projectors. So there are no real possibility of disentangled all these kind of local algebras. There are some attempts to define kind of split property. For instance, there is a paper by Giovanni Valente in 2014, I guess. There are also some results by Doppler and other colleagues, but still, to now, there is no clear understanding of how this is possible. This fundamental entanglement of all quantum fields represented by local algebras will show the relational structural character of the theory. And for instance, in the 2013, Vincent Lam suggested exactly this kind of ontology, and he wrote that the ontology of algebraic approach to relativistic quantum field theory is an ontology of entangled structures, understood in the sense of network of entanglements relation among quantum fields. Now, to me, of course, this definition is quite interesting, but also too abstract, because it will give you, Lam will never give you a clear insight of which is the real physical content of the system represented by those local algebra or the local algebra. And also, it's important also to understand that when we try to spell the ontology in terms of local algebra, more concrete local algebra and their representation, instead and rather than just look to the global algebra, we will have again the problem of inequivalent representation. For when we have two representations of the same local algebra and we cannot decide which is the correct one, we will have the same problem again that we already seen for particles and fields. There are some possibility in this sense. I worked a bit on it in my dissertation and in a paper some year ago. That is that to use the super selection formalism, which is already, I mean, discussed by, for instance, Stephen French in 2012. In any case, this formalism was originally proposed by Doppler, Hag, and Roberts in 1971 and 1974, and the idea is that to apply some physical criteria, and this is, I mean, would be interesting to understand why they use the term physical and consider the fact that in their paper, physical is something like mathematically, in that sense, not really mathematics, but it's not really physics either, in a sense. In any case, with that kind of approach, it's possible to solve some of the problem, but again, they are not conclusive, and so maybe also structural realism is not the most compelling option we have on the table. And so we arrive at our conclusion. And so when I say that we have no particle, neither fields, and we say, okay, maybe they are not the correct ontology, we should adopt an ontology in terms of structures, but maybe we have another option on the table, and the option is maybe we just have to recognize the fact that particles and fields could not be considered as the fundamental entities described by the theory, and maybe at this level the search for what is fundamental is ill-posed in a sense. So in continuity with non-relativistic standard mechanics, standard quantum mechanics, we can say that perhaps this kind of underdetermination between particles and field could, in a sense, be the could inherit the old, let's say, old duality between wave and particle. So maybe it's the same kind of duality, it's the same kind of undetermination, and the fact that we cannot read a unique ontology, a fundamental unique ontology for the theory, could be an insight of the fact that maybe the two are useful. Because, for instance, when we discuss what we find in our particle detectors, we can describe the results in terms of particles. When we want to deal with interaction, maybe sometimes it's convenient to talk about fields. And this kind of underdetermination that would lead to complementarity was already suggested in a very interesting paper by Michael Redded in 1982. And the idea is here to consider the fact that there are no possibility to choose among one of these ontology. And maybe we can say, considering also the Redded theorem above, that one reading of the theorem is, okay, the problem of the particle could be also the problem of the field. So there are none of them. But another reading could also be that that theorem prove in a technical way the intuition that Redded suggests in his paper, that actually these two formalisms are in a sense equivalent, are two representations of the same physical system. I would say, I mean, it's quite different, but in a sense we can say that, for instance, we have just the same situation that we have, for instance, in quantum mechanics when we use the Schrödinger representation or the Heisenberg representation. We have two representations taking elements of the theories prior to others, but actually are, I mean, ipso facto the same theory. And here, the same. So we could have a different understanding of the same theory, and maybe the only possibility to decide among them is just a matter of convenience. So when we want to discuss some kind of experiment results or some kind of interaction picture, for instance, that in particle terms is not so easy. And so our proposal, of course, is a working hypothesis, and we still need to work on it, is that maybe we have not to throw away completely the notion of particle and the notion of field and go to more revisionary kind of ontology, but we have to just, I mean, using again an old idea that was once proposed by Niels Bohr and then was again suggested by Redded, and maybe can be still useful to understanding the ontological content of our physical theories. Thank you.
Thank you so much, Emanuele, Mauro. We have plenty of time for questions. Matteo Morganti first, then Otaku.
Thank you very much, Emanuele and Mauro. I'm still thinking about it. I'm not entirely sure it's the same situation that we had with wave-particle duality, because in that case, it seems to me that we had some actual results, in the sense that if you use the concept of particle, then you can successfully represent something about reality, but not everything. And some other parts of reality, they behave like waves, so we have to use both frameworks. And either we are instrumentalists, but this is not the option today, because you want to be a realist. And in that case, what is your ontology? So the question is open. And in this case, I think the situation is even worse, because you started off showing us in a convincing way that if you work with particles, you don't really do anything, because it doesn't fit the empirical evidence. And then you switch to fields and you have the same problem. And on top of this, you have this equivalence between the two frameworks. So how can you solve the problems by going complementarity with two concepts which, taking in isolation, they don't work? So
you
get my question. Yeah,
I understood.
Even if you don't want to be an instrumentalist.
Say something.
Sorry?
I'm assuming that you don't want to be an instrumentalist. Otherwise, there is no problem, of course.
Okay, I mean, to me, the idea here is that when we consider those problems, we have in mind the idea that we are searching for the fundamental ontology of the theory. So, of course, if we want to describe the fundamental ontology of the theory in terms of either particles or fields, we will have to respect certain ingredients of the notion itself. So, for instance, particles should be countable or should be localizable in that sense. And okay, if we don't consider those ontology as fundamental, and we just, I mean, use those ontology to interpret our physical theories, we can have, a benefit also to consider both the ontology, just because we can have an instrument, a tool to understanding what, for instance, Red Hat called the particle grain that we have in the acceleration of our labs. So, for instance, when we detect a particle, there is that point of the photographic lab. So it's not easy to interpret that result in terms of field, of course. And exactly, in a sense, what we can have in terms of the double slit experiment. So if we look at the interference of the waves, we can have a field interpretation, but if we consider the bullet point, we can also have a particle interpretation. And again, I think that it's possible to say the things also for what concerns quantum field theory. Maybe it's not so realist as I think, so maybe it's in a kind of way an operational move, but actually it's what I think that we can read from our theory.
If I can add something, within the non-relativistic context, I think there is a definite relational description, because depending on what you ask to the quantum entities, you have certain results. For instance, you use a double slit, and then you have a wave-like phenomenon. If you want to localize, then you have this little point in the fluorescent screen. Now the question is, can we go relationalist also in the quantum field theory case, so that whatever you get depends on the kind of questions that you ask to the system? And I think that we were suggesting that both ontological accounts were important, but we don't go fundamentalist in the sense that it's not the only picture is not just particle, it's not just fields, but you need both. And you need both in different circumstances, which doesn't entail that we go instrumentalist about the theory. So that it depends on the kind of situation that you're facing. But this doesn't mean that you don't have any ontology. You don't have a monistic ontology. Basically, the idea is that you need both. And so sometimes philosophers try to look for one single element and explain everything. And maybe there is no such a thing. Maybe the world is much more doubled than we think. So one lesson just could be, well, don't look for one fundamental entity. We need both. And maybe we need both in different circumstances. And the circumstances somehow determine the kind of entity that you get when you have it interact with, say, measurement apparatus or things like that. So why should we look for only one fundamental ingredient? Maybe that's the mistake behind the philosophical attitude.
Thank you very much, you guys. Now we have a question from Otávio Bueno.
Thanks a lot, Mauro Emanuele, for the really interesting talk. I actually had exactly a version of Mateo's question, and I have similar concerns. So let me ask you something different then. When in light of, for example, Malamud's theorem, how can we then square quantum field theory with experience, right? Given that when we test the theory, obviously we don't detect fields, right? We detect some particle-like things, right? So what would be the story in assuming that result?
Okay, there are some technical tools that allow to localize particles unsharply. So the idea is that when we want to localize particle, we can have, for instance, several notions of localization that are not so rigid as, for instance, Malamud's one. And actually, this kind of localization notion can be used in conventional quantum field theory, which is the theory that we use, for instance, to what is called particle physics in a sense. And in that kind of situation, we can localize particle, but not in a sharp way. So the idea that particle can be localized at a space-time point, at a single space-time point, is not possible either. But in conventional quantum field theory, not the algebraic approach, it's possible to define different notional localization. It's interesting in any case to also notice that there are a lot of literature about this notion of localization, and there are several possible definitions, but there is a very interesting result of Alvarson and Clifton that prove that if we use all this kind of localization notion and we use a generalized version of the Rich-Leader theorem, at least in the algebraic approach, no localization at all is possible. The things are quite different for conventional quantum field theory, in which, of course, Rich-Leader theorem does not apply. Yeah. So in that case, we will have kind of working notion of localization that are exactly the one that we use in our particle physics.
Mm-hmm. Doesn't that establish that there is something fundamentally troublesome with algebraic quantum field theory?
Well, yes. I mean, of course, it can be an objection to use this approach in order to read out our ontology or philosophical insights. But in any case, it's also true that there are kind of perturbative algebraic quantum field theories that kind of, starting from the real original idea of Rudolf Haag and Kastler, try to implement in the theory, in the algebraic approach, also all the tools that we have in the conventional quantum field theory. So, for instance, like the S-matrix, perturbative approaches, renormalization, and all this kind of stuff. Of course, it's an open project. It's not still completed. It's not yet completed, sorry. But in a case, I am confident in the fact that also for the notion of localization, at least in a sharp way, there are work of Detlef Buchholz on that. It's not so impossible to define an unsharp definition of localization also in algebraic quantum field theory. But I have to study more on that, of course.
Thank you very much.
I want to add something to Ottavio's question, namely, I think you're right, Ottavio, and I think Matteo is right. There is really a conflict between what we observe and what we measure, because we always observe localized stuff. Mm-hmm. I mean, when we look, you always look at something that is particle-like. You don't measure fields. I mean, of course, you measure field strengths, and that's also something that relates somehow to the possibility of localize your measure. So whenever you talk about measuring something, you have to talk about something that you can localize, right? Unless, of course, you can use laws to extrapolate what you measure here and then see what you would measure over there. So I think the concept of particle is somehow that you need, something that you need if you want to introduce the idea of measurement. On the other hand, the notion of field seems to be the fundamental notion. So I'm not completely agreeing with Baker's result, but Malamud is certainly in contrast with what we observe in the lab. There's no question about that. Now you're talking about trapping atoms, single atoms trapped in a small, very, very small region. So what happens to field? So there's really something that needs to be studied by philosophers. My intuition that particles must emerge when you make a measurement, because fields also are localized. I mean, of course, fields can be in space-like related region. Of course, that's true, but you need measurements as well, and that's where the particle motion. It's a little bit like a non-relativistic quantum mechanics. So that's really something that needs to be pondered on, I think.
Yeah, I couldn't agree more, Mauro.
Now, Chris, would you?
Yeah, actually, I had more or less exactly the same question than Matteo. So let me try to push it a little bit more and rephrase it in terms of realism and anti-realism. So I would say that an anti-realist scheme just requires mathematical formalism and certain phenomena described by the formalism. That's it. And the realist wants more. He wants a representation of what's really going on according to it. Now, the Boolean scheme, the Boolean solution, I would characterize as strictly anti-realist, not as a realist representation, because as a matter of fact, it's a way of mixing inconsistent representations of the same state of affairs, and that these representations are dependent on the choices of the subject regarding the measuring setup. So before the subject provides a choice, you don't have a representation of a state of affairs, and for me that's kind of very anti-realist. I would argue that a realist thinks that there is a state of affairs, and I'm going to try to relate to it through measurements, through the mathematics, through the concepts. So my question is in this direction. I mean, even regardless of the fact that algebraic quantum field theory has a lot of problems in itself, because it has a lot of problems to connect to what physicists call quantum field theory. I mean, that's not it. It has completely different. So how would you characterize? I mean, your standpoint is a realist standpoint, but what I see, this, as Matteo pointed out, and also Ottavio, is that you end up in a completely anti-realist justification of your attempt and an anti-realist solution.
Can I reply to this? In the case of Bohr's theory, I think you have to realize that he was really a relationist and not an anti-realist. Namely, if you remember, he always wants us to consider the whole experimental apparatus, and insisted that you cannot attribute a monadic state property to a quantum entity unless you immerse it holistically in the whole situation. So I think Bohr is really a relational realist, not an anti-realist. If you want, you can read Bohr as a dispositionalist. So particles have, or entities have dispositions to manifest themselves. Entity like electrons, if you want, have the disposition to manifest themselves as particles, depending on the kind of interactions they have. Or entities like electrons can manifest themselves as waves, depending on the kind of relation that the entity, which is a disposition, basically has with the environment, so to speak. So if you understand Bohr by reading his, which is not really Bohr, but that's the way I would read it, by insisting that you need some sort of relational story that you have to give in order to understand how this dispositional entity is going to be manifested, then I think you can still defend a realistic position, even though sort of different realistic position. The idea is that you cannot talk about a single quantum entity unless you introduce some sort of quantum entity that interacts with the fair. In the case of the quantum field theoretical contest, there is certainly a difference between what I just said about Bohr and what we said about, say, the consequences from an ontological viewpoint. But again, I think you should play, or we should play the same game. Namely, you could try to say that fields have this disposition to manifest themselves as particles when you measure, because particles, or at least localizations, are necessary to make sense of measurements. So fields may certainly be considered as dispositional entities, which then manifest themselves in a particle-like manner, but at the same time, of course, they can also manifest themselves as field whenever you have interactions. So you can go realist about fields, or even quantum entities, if you talk about relational quantum, relativistic quantum mechanics, when you use the language of dispositions. So that you can actually say that there is no contrasting property, because electrons are both particles and waves. There's no contradiction, because they have these two properties somehow at the same time. And I would say the same about the quantum field theory case. So whatever the entity, fundamental entity is, there is a propensity, which is probabilistic, to manifest itself as a field or as a particle. Of course, that depends also on the kind of relational contract in which you are. There is something that Rovelli's view is correct about, namely, quantum theory is a relational, deeply relational view of the world. You cannot talk about a system in isolation. I think that's the lesson that Bohr taught us. I mean, Bohr said, you cannot really think that there is something that exists independent of the measurement. Measurement don't reveal pre-existing properties, which means that you cannot abstract and separate the entity from the measurement apparatus. I'm sorry, I went too far. Maybe, Emanuele, you want to add something, and there are other questions that